a second. What I just described is a zero-knowledge proof that you are not on a banned list, right? Anybody who maintains,
Also an assistant professor of computer science at the University of Maryland, Ian Miers. So, Ian, happy to have you here and excited for your talk.
Okay, so hi, everybody. My name's Ian Miers, professor at the University of Maryland, and I've spent the last about 10 years working on zero-knowledge proofs for blockchains, starting with how do you add privacy to Bitcoin. This was in 2011 when I started working on this, and then it was like, well, let's use zero-knowledge proofs to do this. And so that led to ZeroCoin, it led to Zerocash, and then the techniques that are now in Zcash, in Tornado Cash, and basically every single other second-gen privacy coin that's coming online now. And so that's been fun. It's been really interesting. I was sitting at the band last night for DevCon outside, and there was a musician there who was singing, and the lyrics had something to do with zero-knowledge proofs. I was a couple of beers into it, so I didn't catch all of them. But okay, one, that's a really weird musician. But second of all, 9 years ago, nobody in blockchains would have had any idea what zero-knowledge proofs are, let alone would they have been singing about them. So it's been an interesting, nearly decade of work on this stuff. But the question I've been thinking about now is, okay, what happens if privacy isn't the driving thing for zero-knowledge proofs and adoption? What else are we going to use them for? So I gave a talk at DevCon yesterday on this, on like, privacy is dead, scalability is boring, what are ZK proofs good for? But I didn't really give a technical answer. And so what I want to do here is cover some work on things you could do. And this is work that's mostly been done by my graduate students. Right? So they did all the hard work here. They wrote all the slides. When I present them, the reason it's going to be awful is because I'm basically just taking their slides and using them. But the premise of this is that we see a lot of noise in this space about zero-knowledge proofs, but most of this is for zkVMs, for zk rollups and scaling. And this is great work. It's really impressive stuff, and I'm really excited to see it come out, and the languages for zero-knowledge proofs. But the problem is, they aren't really zero-knowledge. Right? They don't actually use ZK to hide anything. Rollups compress transactions. They make a blockchain scalable. And to do that, you don't actually have to hide what's going on. Right? You don't have to hide your data. Worse than that, actually, they're not going to hide your data in all likelihood. Right? Every single zkVM, every single ZK rollup that's being built now is trying to get scaling. And in the process of doing that, that's great, but they won't give you privacy. Right? Most ZK rollups leak the Merkle hash of your data. They also produce a zero-knowledge proof that might reveal some things, but just think about this Merkle root they're publishing. Well, that Merkle root is over data that belongs to you, and it would be like publishing the hash of your password online. Even if I give you a zero-knowledge proof about that password, right, say that it meets some absurd password policy, it has a capital letter, 3 symbols, and a couple of emojis in it, I give you that as a zero-knowledge proof, it doesn't change the point that you publish the hash of your password, and somebody can go guess and see, hey, what was your password? Was it dog? Was it cat? Was it your mother's maiden name? And similar things will happen in ZK rollups, so they're not really doing zero-knowledge. They're sort of nutritionally deficient here. And this is fine for what they're trying to get, but from my standpoint, it's kind of boring, because ZK proofs, the cool thing about them is that they're zero-knowledge. They hide what's going on. They hide data from people. And ZK rollups kind of ignore that cool bit of it. So what do you do with a zero-knowledge proof? What is it good for? There are a number of different options there. In this talk, I want to talk about 2 things that my graduate students and I and some other collaborators have been working on. And these are both papers you can find online on IACR ePrint. So the first one is a paper called Zkcreds, which is flexible anonymous credentials from ZK snarks and existing identity infrastructure. And so the idea here is you need to prove all kinds of things about yourself online. Right? You go to a website, you need to prove you're not a robot. Right? Maybe Elon Musk is asking you questions of whether you're contributing to Twitter's bot problem. You need to prove you're not a North Korean money launderer if you're using Tornado Cash, or you did until the US government shut it down. You need to show that you're over 18 to view restricted videos in many countries in the world. And these kind of things are hard to do without identifying yourself fully. So maybe you want some privacy here. And this is a long line of research in academia called anonymous credentials, looking at this in a centralized standpoint where you had trusted issuers who would issue anonymous tokens. The question here is different. Can we make a decentralized version of this? Can we make a version of anonymous credentials, a way to prove who you are, without having trusted issuers? And so the thing we actually built, and you can go download the code that's up there to do this today, is a system that takes any kind of identity assertion you want. The example we used was a US passport, and allows you to build a zero-knowledge proof that you have this passport, issue a credential on it, and then later prove that you're over 18 because you have a passport that says that, without ever revealing anything about who you are. Right? So this allows you to actually bootstrap an identity from any set of credentials you want. Right? It's a flexible framework, but this is the proof of concept here. And this is like real. Right? There's actual code. This isn't like pie in the sky. It takes about 150 milliseconds to do the authentication. So you can show up to a website, and 150 milliseconds later, you can give them a zero-knowledge proof that says you were over 18 without revealing anything else about who you are. Right? You could also prove to them that you're over 21. You can prove them that your age is a prime number. It doesn't care. This is a flexible framework. You can write a circuit to do whatever you want. But it works. And so there are two interesting points about this. The first is, again, this requires no trusted issuers. It doesn't require us to collaborate with the passport authority. It doesn't require us to get some new person to use some newfangled cryptography. This works with an off-the-shelf passport. The second interesting point is, who here has Netflix? Who here has an actual Netflix account and isn't just borrowing like their parents or their friends from grad school? Okay, that's one person. Right, everybody lends out passwords. Everybody lends out credentials. Right? And a real major problem for anonymous credential systems is that it's really easy to lend those out to other people because they're anonymous. The entire point is you're meant to be private. So if you take the setting of, say, age-restricted videos, one person, like your cousin who's 25, wants to look cool, lends you their credential, and like all of your friends are going to be able to use it to access like, violence-restricted videos because they're just going to share the credential around. And you're going to have no way as a platform operator to know this because the credentials are anonymous. You can't tell that it's cloned. But it turns out, through some actually pretty simple cryptography, and I mean like high school algebra level stuff, we can make a system where if you clone your credentials, it reveals who you are, and we can ban them, and we can ban your account. And so this is a cloning-resistant anonymous credential. So how does this thing actually work? Let's say you wanted to prove to a website that you're over 18. It's a multi-step process. First, you need to register your credential with the credential provider. And since this system is meant to be decentralized, the only thing the credential provider has to do is be able to maintain a list. Right? So this could be a single server. It could be a permissioned blockchain. But you can also run this thing on Ethereum. If gas costs weren't insane for storing data. But you can do it. And so what you do is you take your passport. We wrote a little Android app, and this is grad student code. This isn't fancy, full-blown stuff. It's a prototype. But you take your Android app, you scan the passport. There's an RFID in your passport that has a digitally signed certificate on it, and that app converts the signed certificate into a zero-knowledge proof that you have a credential with your name, birth date, nationality, and everything else that's in your passport on it. And so you take that and you make this credential. And then you need to upload this to the register. And you literally just post this thing on a blockchain, right? You take your credential, the proof that says you actually have it for a passport, and you post it up to, say, the Ethereum blockchain or the Aleo blockchain or whatever you want. And the blockchain checks that that zero-knowledge proof is correct, and it sticks it in a Merkle tree. So far, so good. For those of you who know how Zcash works, you can probably guess what comes next. If you now later want to go to an actual website after you've registered and prove that you're over 18, you need to do a separate zero-knowledge proof later. And this one is quite simple. You prove that you have this credential inside the Merkle tree. Right? So you prove that this thing exists. This is going to have your actual birth date in here. Right? So you don't want to reveal it. You just say, I have a credential in this Merkle tree. You verify the path inside the ZK snark. That exists, and then you prove whatever it is you wanted to state about your identity inside the zero-knowledge proof. So you're going to produce a zero-knowledge proof that says, this credential is in here, and it has a birth date in it such that I am over 18. And that is all you're going to reveal about yourself. And so this will convince a website that you're over 18, that you have a passport issued by, in this case, the United States government, that you are over 18, but reveal literally nothing else about you. And the zero-knowledge proof guarantees guarantee that you can't figure anything else out. The authentication process leaks nothing else. Might have to worry about hiding your IP address if you're visiting it using a web browser, but that's not our problem. Credential scheme hides who you are. So that's the basic bits. That's the, building this out of kind of Zcash, eCash techniques. But then it gets kind of cooler. As I said, there's a problem. If you have this credential, you can lend it out, right? If your cousin has a proof that says they're over 18, they can lend it to all their friends, and then everybody's using it, and you're bypassing this age check. So how do you get around that? What you can do is you can rate limit how many times this credential can be used. You pick a reasonable number that no one person would ever exceed, but that if you hand it out to your 20 friends, that'll actually go over the rate limit. It's the same way that if you're using Netflix, right, and 3 or 4 of you sign into the same account at the same time and try to view videos, Netflix tells you, nope, no good. Same thing here, except we can actually identify you even though you're anonymous. And so the trick is, as long as you're underneath the rate limit, you're going to be completely private. But the moment you go over it, we can identify you completely, and then actually we can delete your credential off the list and revoke it. So the way this works is we associate with each authentication attempt you make a double spin prevention tag, right? So it's a rate limit tag, which is actually 2 tokens, token 1 and token 2. And these are both random. They are produced by a pseudorandom function. And what happens is every time you do this, you have a counter. And we're going to limit you to, say, 10 authentications per day. So that counter is supposed to be less than 10. So for each authentication attempt you produce, you have to prove that that counter is less than 10. Each time you do that, you produce these 2 random tags. There's no privacy problem here. If somebody tries to authenticate an 11th time, say, for example, because they shared the account with someone else, then they're going to have to repeat that counter. Because we're still proving it's less than 10, you just had to try again and again. So now you're going to repeat the counter, and then that random number in token 1 is going to repeat. OK, that doesn't help us. That's just a repeated value. We know you shared the credential, but we don't know who you are, and we might not find out that you did this until after the fact. But the interesting thing is that token 2 here is going to let us actually de-anonymize you if you've repeated this counter, if you've double spent this thing. And the reason for this is because, well, token 1 repeats, and it tells us, hey, here's this guy with the same ID twice. Token 2 is subtly different. And so what you have is an encoding of your username and then some random noise here. And the way you should view this is this thing is being randomized by that. And as long as you only ever show this thing once, it's your username plus a random value. Nobody can figure it out. But if you do this twice, and you get 2 different ones of these with 2 different versions of this equation, then it isn't random anymore. It actually looks like something like that, where you have this nonce, this PRF value we don't know, and you can sort of abstract this out, ignore all of the cryptography, just think of this like high school math. You have these 2 things, token 2 prime. One of them is your username plus 42 times y, which is the PRF value. One of them is your username plus 99 times y. Right? That's literally the same thing. I'm just removing the cryptography because we don't need to think about it. And, well, this turns out to be a thing we can solve with high school algebra, I think. I haven't taken high school algebra in a long time, and my Linnell class in college was at 8 in the morning, and I slept through it. But my grad students swear that if we do this, you can use this and solve it to get the identity of what's going on. And so this is, rather cool. We have an anonymous credential system. You're completely private. Nobody has any idea who you are. But if you reuse this thing too many times, through really basic math, we can find out exactly who you are, and then we can go ban your account. And so we have a rate-limited anonymous credential. You can use this for selling subscription services to videos. You could use this for doing restrictions on how many times you can post on an anonymous forum. You can use this for, well, it's a flexible framework. You can do pretty much anything you want. So that's one idea, right? This is the Zkcreds approach, right? We have this flexible anonymous credential scheme where using an existing US passport or anything else you want to fit into it, we can generate credentials about your real-world identity that then can be used online anonymously. So that's one thing that zero-knowledge proofs are good for. This is a paper that's up on ePrint. It's currently in submission to a conference. There is code on GitHub, but you can find it. We should be putting up a more updated copy soon. So that's one application. The other application that we've been working on, and this was actually published in May of this year, is a thing called Snarkblock. And the idea here is that we want to allow people to have anonymous communication online or pseudonymous communication across multiple different forums where there's no way to link your account from one forum to another. But if you do something a little too snarky, a little too trollish, the operator of one of these things can ban you. And even though you're completely anonymous, you lose your ability to post anywhere else that subscribes to that ban list. So this is a way to do distributed moderation for, say, decentralized social media without impacting privacy. This is also joint work with one of my graduate students and Mary Maller at the Ethereum Foundation. And again, they did all the hard work here. I'm just the one standing up on stage talking about it. So as I said, the motivation here is that we want to allow you to have different identities in sort of different circumstances. Your post on a forum about your medical condition, your sexual orientation, your politics, whatever it is, probably you want that to be separate from your posts about like your professional life, your research objectives, whatever else you're doing. Right? Those probably shouldn't be linked together. Like that's a notion of a right to privacy and how humans work. But we also want to make sure that people aren't trolling everybody online. And so this has led to this problem with existing identity systems, for example, in Facebook, where in order to solve the like spamming, trolling, abuse problem, rather than letting you have disparate identities across disparate things, different subreddits, different accounts, everyone does this like you have one account you have to sign into on different forums. Facebook requires that you use your real name for it, et cetera. And then this is the thing that ties all of your accounts together so that they can do moderation. And so there's this seeming challenge between do you want to have strong identity requirements on the one hand to prevent people from trolling and to be able to ban accounts. On the other hand, can you let people be anonymous? And the idea with Snarkblock is to try to resolve this question. And in particular, how to make it decentralized. So there's a really cool idea here, and this is not ours. This dates back to 2007 by a paper by Chang et al., that you can actually solve this, at least in theory. You can actually get completely, totally anonymous posting, but still allow blocklisting. You can still block someone. So the scenario here is we have a user, call her Alice, who makes posts on whatever forum they want. In this case, my grad student decided to use the daily science fiction forum as an example. And they are going to post things. And some of them may be kind of, things that will get them banned. Right? So like a message that's just like a low-effort review, 2 out of 5, where are the elves? I don't like this. I think this is a Lord of the Rings reference, but he never really explained it to me, so I don't quite get it. But you're going to post a message here. And the idea is that this message should be anonymous. There should be no association with the user's account. But later, if that message gets banned, we're going to associate with each one of the messages you post a random tag. And there's a list of blocked users defined by the tags. And we can ban you with it. Or more correctly, if you're posting multiple times, you can prove that your previous posts were not banned. So every time Alice does a post, she is going to prove that none of her previous posts were banned. So in particular, that none of the tags associated with any of her other posts were banned, and therefore she's still in good standing on the forum. And this is private because these tags, as we'll get to, are random looking. And this idea is sort of, in my mind, kind of revolutionary. It was sort of eye-opening when I read it. But the problem is it doesn't really scale with the techniques that Chang et al. Were doing. If you're familiar with how zero-knowledge proofs work, these guys were not doing this with snarks. Snarks didn't really exist at that point. They were doing this with like basic Sigma protocols. So those proofs end up being linear, and the entire size of the blacklist. They're huge. They don't work. They don't scale. So we took this as a starting point, and we wanted to improve on it. And so the details of how this protocol works, in this setting, we assume that Alice has a master key. Right? So this is supposed to be some Sybil-resistant thing to get. Right? To get this identity, Alice might have had to fill out a CAPTCHA. She might have had to actually show her real identity, like passport or something, to some authority. She might have had to pay some amount of money, registered a phone number, any number of Sybil-resistant schemes that you've seen if you've done accounts online. Whatever that account is, she has one of them. It's valuable. We assume that she can't easily make more. And so the actual process of posting, if there's nobody on the blacklist, is that Alice generates a tag from a random number evaluated on a PRF, pseudorandom function, keyed on her secret key that nobody else knows. And then she generates zero-knowledge proof that she knows that key and that tag is properly formed. So this is just, here's a random number. It's deterministically derived from my identity in a random way. So that's the proof about the tag. And if there's nobody on the block list, if Alice wants to post her snarky message of there are not enough elves in this piece of fanfic or whatever it was, she just produces that single thing, which is here's the nonce, here's the tag, here's her post. And this shows that she's authorized, the forum can accept the message. But what happens if there are banned users, right? If there have been posts that were offensive and previous tags from previous messages have been added onto the account? Well, in that case, same process goes through, but now Alice produces a slightly different proof, which is in addition to her PRF tag being correctly computed, she proves that for every single entry on this block list, and the block list entries are a tuple of tag comma nonce, right? The nonce being the thing that's used to produce the tag. She proves that that nonce, evaluated with her PRF and her key, is not equal to the tag. So you can think about this as, in very complicated cryptographic terms that academics will want to use, for every single thing on this list, Alice proves in true sort of Bart Simpson manner, I didn't do it. Right? She just loops over and says, that one's not me, that one's not me, that one's not me, that one's not me. Right? It's a linear proof. It's linear in the size of the ban list for her to prove it. But, spoilers, using zkSnarks, we can at least make it fast to verify. And so you loop over all of this, you produce this proof, and again, if Alice has not been banned, she can still post. And she's still anonymous here, right? This tag is random. It reveals nothing about her. The proof, because it's zero knowledge, reveals nothing about her. All the server learns is that she's in good standing. On the other hand, if she was banned, if one of those entries was for an item she'd produced, a post she'd made, then that proof down there wouldn't go through. Because for one of these things, like say it was the last one added, she'd get to that one and she'd try to prove that PRF sub k of her nonce is not equal to that tag. And it actually would be, because it was her tag. It was the post she made, and so she wouldn't be able to authenticate. And so this is the sort of approach we build on. But the problem is that these zero-knowledge proofs are, naively, if you do this, the proof is linear in the size of the block list. It takes linear time to verify. And so this means a server that's processing these is really easy to DOS, because it basically, DOS attack has a quadratic impact, right? For each spam post that gets banned, you have to do linear work. So in aggregate, n times n squared, you have quadratic problems. So we would like this to be succinct. And so the approach that we worked out was to divide this list into chunks, and then basically do the proof chunk-wise. Did this with graph 16 proofs, to be precise. And then we aggregate all of the chunks together. Right, so this was using an inner pairing product type argument. This actually required some pretty tricky bits to make this work, because if you're familiar with proof aggregation techniques, they basically assume that all of the inputs are public. And so the problem here is for each one of those chunks, we have to show that Alice is making this proof with respect to her consistent identity. But the identity has to be secret. And so now we need to do a hidden common input aggregate proof, that's what that stands for, across all of these. So we had to figure out a way to have chunk 1, chunk 2, chunk 3, chunk 4 proofs that we aggregated together with an IPP, but showed that they all shared the same hidden value, which is Alice's identity as an input. And so we managed to do that. That was actually the sort of core cryptographic element of the paper, and the main thing Michael, my grad student, spent most of his time working and implementing. But the net result of this is that because this proof works, same thing happens here. You can produce a proof that you're not blocked, but this proof is logarithmic in size and logarithmic in time to verify for the server. And so this works out. The chunk proofs are somewhat annoyingly large. You have to compute these realistically offline, like before you try to do an authentication, so there's some cost to keeping up with this. But it's still a lot better than the previous state of the art. And it's actually sort of, in my opinion, almost practical. The limitation of this is that you have to compute a bunch of these proofs in advance. So there's a cold start problem. I'm hoping that recursive proofs might be able to fix this. Here's the really cool bit about this. So that was a lot of math, right? Ignore all the cryptography for a second. What I just described is a zero-knowledge proof that you are not on a banned list, right? Anybody who maintains, the list is permissionless. It doesn't matter how it's maintained, right? It's literally just a list. So that means that anybody who's running a server, anybody who's running a decentralized system can maintain their own ban list where they put ban posts for whatever reason. Point one. Point two, once you have that ecosystem of lists, anybody else who wants to can subscribe to them and use them to decide who they're going to ban on their forum. So like if you're on subreddit 1 and you want to go to subreddit 2, they can subscribe to the ban list from the other one, but both sides will still be anonymous. And all you have to do is literally like copy and paste the list. Right? You can mix and match these lists. You could have a list of people with explanations for why that post was banned, and you could decide that you take some posts that were banned for certain reasons, say for offensive trolling behavior, but not for other reasons, like, say, political positions. Right? You could subscribe to one or the other of these, you could mix and match the things, and you can keep this entire thing in a completely federated manner. Right? The one requirement here is that you do need some way to get Sybil-resistant accounts. Actually, it occurs to me that this was my grad student writing these slides before we wrote the last paper that does the, here's a ZK proof over a passport. So actually, you can use that to get Sybil-resistant accounts in a kind of cool way. But it's still a limitation. We do support federated identities as well, right? So it's not just a single source for that key K that Alice has to register. There's actually a somewhat clever piece of little cryptography in there that lets you have a bunch of different identities and not reveal when you're authenticating to a forum which one of these accounts you signed up with. Right? We just know that you have a single one of these. So that's basically it, right? This is like an interesting idea. We can do ZK proofs over ban lists, and we can federate the ban lists. This was a first attempt to do this with ZK snarks. I think you can do far better and more efficient ones, but it's an interesting answer for what ZK proofs are good for. And so that's it for my content portion of this. So I think I would just take questions now.
Thanks. Hi. So I understood that in the block list, there are tuples of nonces and tags. Mm-hmm. So Alice might have one of those tuples that belongs to her. But isn't it sufficient for her to choose a different nonce?
No, right? So the nonce is, when she authenticates, she picks the nonce. It's random. But when she's doing the proof that she's not on the ban list, that nonce is fixed, right? So there she can't change it. Right? She could change it the next time she authenticates, but that just generates a different tag for the current post she does. That doesn't get her out of the one that got put on there that banned her if she was banned.
I see. Okay, thanks.
Yeah, hey Ian, thanks so much for sharing. I have more of a logistical and conceptual question. Mm-hmm. So towards the end, you mentioned that you can enable a published and federated ban list that can be shared across different platforms. Couldn't someone just scrape addresses and test that against the ban list and then figure out from these addresses and that testing who are the people being banned?
No, because in order to do that testing, you have to have the secret key, the user's key. So actually, I completely glossed over the actual properties here. In this system, you're anonymous before you're banned, and you're even anonymous after you're banned. Nobody learns anything about you except for the bit that you're no longer allowed to post. That's technically how the security game's gone. But yeah, that's a good idea, but it wouldn't work because you won't have the secret key.
Great, thanks.
Yeah, I have a question. Like the third case that generates a chunk here, sorry.
Okay, sorry, yeah.
The third case that generates the chunk once you get banned. Mm-hmm. How is this chunk generate? Because you say that the proof of the chunk is pre-generated before, right? Or am I missing something?
So the idea in this model is that the ban list exists. It's being updated periodically. So you have a proof for the previous chunk of the ban lists, And then when you authenticate, if there's been a change in it, you're going to have to generate one new chunk proof for whatever the live update is, whatever the staleness in your cached copy.
Okay, thanks.
Over here?
Yep.
So can chunks be adaptively changed depending on load?
Potentially. I remember we looked over this and we sort of punted on whether it made sense to do or not. You would have to have pre-generated the circuits for the different chunk sizes, but yes, you could dynamically adapt that if you wanted to. Yeah, it should work, and it should be safe from an anonymity standpoint. Anybody else? OK, well, then just as a recap, what can you use zero-knowledge proofs for? Anonymous authentication that gets you banned or your identity revealed if you use it too many times, and banning trolls on the internet while keeping yourself private anyway. So I think it's kind of interesting. Somebody should run with it.
All right, thank you very much, Ian.